Hello everyone, Assalamualaikum and a very good morning. I'm Amebi Mamanan. So this is our group member Muhammad Amizan, Ishaq Fuzila, Muhammad Faris and Jeremiah Dashan. So I will talk about the introduction. So the introduction, fertigation of the application and fertilize with irrigation water allows the application of modest amount of fertilizer in each fertigation event, allowing for more fertigation frequency flexibility. There are two sorts of pipe layout that can be used for watering, straight line and closed loop. Uh, these two alternative arrangement will result in difference in flow rate and water volume obtained by each plant. This circumstance will eventually have an impact on the plant quality. So the another introduction, the volumetric flow rate, also known as volume flow rate, rate of fluid flow or volume velocity, in the volume of fluid that pass per unit time in physical and engineering, particularly fluid dynamic. It is commonly symbolized by the sign Q, occasionally V. Q equal to V times A, where V is flow velocity and A is cross-sectional vector area. So the introduction, that is the Bernoulli equation, can be thought of as a formulation of the energy conservation principle for following fluids. The reduction of fluid pressure is location where the flow velocity is enhances the qualitative phenomena that is commonly characterized as the Bernoulli effect. This reduction of pressure in a flow rate constriction may appear paradoxical at first, but it becomes less so when you regard pressure as energy density. Kinetic energy must grow at the pressure. At the expenses of pressure, energy in the high velocity flow through the constriction. So this is the formula. So P1 is the pressure energy. So PV is kinetic energy per unit volume, and PGH is potential energy per unit volume. So the last of my part is about the objective. So in this objective, we learn to perform the experimental and simulation flow exercise in hose pipe to get inlet and outlet pressure, in the velocity, to get the density and viscosity of the water, get knowledge in the Reynolds number, and the last one is to analyze pressure variation in hose pipe over a specific pipe length with two different configuration, that straight pipe and the closed loop pipe. So that's all from me. Thank you. Assalamualaikum.
Assalamualaikum. My name is Ishamin Mufzila. I will explain about the configuration of the experiment. The first of configuration is straight line water hose configuration. We use 5 meter straight pipe and 10 nozzle for this first experiment. And the second one is closed loop water hose configuration. We use 5 meter loop water hose and also same 10 nozzle. The equipment we use in the experiment is the connector pipe. The second one is poly pipe, 5 meter long, and the nozzle, 10 nozzle. After we run the experiment, we take the data by take time for water to fill 200 ml, and we calculate the flow rate by times the quantity of water divide by time. We get there meters square per second, and we calculate the velocity for the water. We get here 2.358, and also density, kinematic viscosity, and Reynolds number. The second table is for closed loop hose pipe. We get here for the first hole is 18 second, and the flow rate is 1.11 meters square per second. For the viscosity is 1.5719 meter per second, and also the density of water is 1000. The kinematic viscosity is 0.893, and the Reynolds number is 5281, and also same for the all the nozzle. That's all for me. Thank you.
A very good day. My name is Jeremiah Darshan, and I'm lucky Rita SUSA, and my ID number is B09201037. And today for this fluid mechanics assignment, I'm going to present on the calculation. So yeah, it's given that we have found that the density of water is 100 kg per meter cube. The atmospheric pressure is 101.325 kilopascal. The diameter holes is 0.016 meter. Maximum height is 0.67 meter. Time taken 2.45 seconds. Volume is 0.0002 meter cube, and the area, when we calculated, and we got 2.11 times 10 to the power of negative 4 meter square. So for the flow rate, the formula is velocity over time. So the value of flow rate is 8.1633 times 10 to the power of negative 5 meter cube per second, and the formula for velocity is flow rate per area. And after calculating, the value is 0.4059 meter per second. So we have to find the pressure 1, where pressure 2 is given, and it's also equals to the atmospheric pressure, and volume 1 equals to volume 2, and Z1 is 0, whereas Z2 is 0.67 meter. So after using the formula, lastly we will get the value of P1, which is 107.900 kilopascal. So for the straight pipe, diameter hole is 0.003 meter, radius hole is 0.0015 meter, and the area is 7.0686 times 10 to the power of negative 6 meter square. So actually we have 10 holes, but for the presentation I've only taken one hole for the straight pipe and also for the closed loop pipe. So for the straight pipe, I've taken the first hole. Time taken is 12 seconds, and the flow rate is 1.6667 times 10 to the power of negative 5 meter cube per second, and the velocity is 2.358 meter per second. And lastly, for the closed loop pipe, I've also taken the first hole as reference. The time taken is 18 seconds. Flow rate is 1.1111 times 10 to the power of negative 5 meter cube per second. And lastly, the velocity of the closed loop pipe is 1.5719 meter per second. That is all from my presentation. Thank you.
Okay. Assalamualaikum and very good day. My name is Muhammad Hamizan bin Adnan, and I'm going to present about the simulation flow using SolidWorks. So the main objective of this simulation is to obtain data such as velocity, pressure, viscosity, and density by using actual dimension of the pipe. So the first variable that we obtain is velocity, and And as we can see from the slide, the highest velocity we obtain is 1.543 meter per second. So the water flow achieve this velocity at the tip of the nozzle, where the diameter of the nozzle is significantly smaller than the diameter of the pipe. And, and this is the data that we have obtained from the analysis. So here is the velocity for each nozzle, all 10 nozzles, and all of the nozzles have an average velocity of more than 1 meter per second. Some of them are 1.06, 1.02, 1.05, and that is the average value for straight pipe configuration. Next is pressure. The maximum pressure that we obtain is 82 kilopascal. I mean 84 kilopascal, and minimum pressure is 82 kilopascal. Next variable that we obtain is density, which remain unchanged along the pipe. So the value of density is 997.56 kilogram per meter cube. And then the viscosity also shows no change along the pipe, and the value is 0.001. That's all for straight pipe. And next we go to loop pipe configuration. So there's the same density of fluid remains unchanged, and the value is 997.56 kilogram per meter cube. And then viscosity slightly lower than straight pipe configuration and still remain unchanged along the pipe. And then we go to the velocity. So as we can see, the highest velocity that we obtain is 1.12 meter per second. So compared to straight pipe configuration, the velocity in this configuration, the loop configuration, is slightly lower. So this is the data for velocity of loop pipe configuration, and we can see that the value is slightly higher, I mean slightly lower than the straight pipe configuration. So the reduction in velocity might be caused by the bending of pipe, which has increased the resistance along the pipe, making the water flow to have a reduced velocity. So the difference in velocity is 0.2 meter per second between loop pipe configuration and the straight pipe configuration. That's all from me. Thank you.
Assalamualaikum. My name is Muhammad Faris Atib bin Azhar. I will represent my group for discussions. This is our result table. The table shows the data obtained from the flow simulation of SolidWorks for the straight pipes. From the table, average velocity of water at each nozzle is higher than 2 ml per second. The Reynolds number is obtained by dividing the product of velocity and diameter of nozzle with the kinetic velocity. Next is our another result table, which is the table shows the data obtained from the flow simulation from SolidWorks for the loop pipe. From our findings, the average velocity at each nozzle is lower than the straight pipe configuration. The Reynolds number is obtained by dividing the product of velocity and diameter of nozzle with the kinetic velocity. This the comparison of velocity and nozzle. From the graph, we can say that the velocity of water is higher in straight pipe configurations compared to the loop pipe configurations. This is because there is less resistance in the straight pipe configurations. The only resistance in this configuration is the presence of nozzle. The velocity varies at each nozzle. The velocity of water in loop pipe is lower due to the higher resistance. The resistance is caused by the curvature of the pipe, thus affecting the flow of the water inside the pipe. Both configurations efficient with the same amount of nozzle, so we can say that the bending of pipe affects the velocity of the water. For the conclusions, in conclusion, we were able to calculate the flow rate, velocity, and Reynolds number from the experiment. The result obtained from the simulating is slightly different from the actual results. This might be caused by improper executions from the experiment. Finally, we can conclude that the bending pipe affects the velocity of water. Thank you, that's all from me.